spot on time, so here in Europe. So let's start the last session of this workshop, and the last session is devoted again to form factors, and we start with a talk by Dalibor Djukanovic on Nucleon form factors from Lattice QCD. Please.
Thank you very much. Let me first take the opportunity to thank the organizers for putting together this very nice workshop. I learned a lot of new things. I'm not sure I understood everything, but certainly I learned new things, and I hope I'll be able to return the favor and show you something interesting that Lattice has to say about Nucleon form factors. And even though I believe that nobody needs motivation to do form factors in the audience, I'll still try to motivate why we are interested in form factors in general and what Lattice can actually say about them. And I will tell you a bit about the Lattice methods, or the Lattice field theory that is used to calculate the form factors and the challenges especially. And I will show you results, and I have to admit these results will be very heavily biased towards MINES. I will present comparisons to other Lattice determinations, but I will focus on the MINES results. I hope that nobody feels offended by this. Okay, so the quantity that we look at usually is an external current coupled to a nucleon, and this coupling can be done via different currents, and the currents that we look at usually are vector or axial vector currents, but you can also look at strange and at scalar and tensor currents inserted here on the nucleon line. And what we are looking here at is the quark, the nucleon charges, So that is the matrix element of these quark bilinear operators, and these are proportional to the axial, the scalar, or the tensor charges. And we can calculate these quantities on the lattice. And this axial charge is actually very well measured in experiments. So this is a sort of a benchmark quantity. Whatever you do on the theory side, you better get this quantity correct. But the scalar and tensor charges, Lattice can give you a valuable input in constraining beyond standard model physics. And as such, this is an interesting contribution from the side of the Lattice field theory to searches of physics, of new physics. The other nucleon matrix element that we look at is the scattering of an electron on a nucleon via the exchange of a photon. And this is basically the vector current that we look at here. And the vector current, the nucleon matrix element of this, can be parameterized using these two structure functions. One is the Dirac and one is the Pauli form factor, but usually we look at different linear combinations, which are the Sachs form factors, GE and GM. And then we have also heard on the talk before the break that we look at Taylor expansions of these structure functions of the Sachs form factors, for example, at low Q squared. And actually, I cannot see it on my screen now, but we can decompose it into these into this expansion where we have the electromagnetic radii as parameters. And there was, before the break, this talk which already discussed the proton radius puzzle. So there was this EP scattering experiment in 2010, which gave basically this value, which was very precise with the 1% error at that time. And then came along this muonic hydrogen experiment with the spectroscopy measurement, and it was much more precise and gave a much lower value. And in the meantime, there's this JLab PRAD value, which is again a bit lower. And the question is if Lattice can actually have a say in this, and I will tell you in a moment what Lattice can do for you for the proton radius. The Lattice side, I have this one slide introduction. I think this cartoon here is already very familiar to you. So in principle, the lattice is nothing but the discretization of spacetime, and you put the theory on a hypercubic lattice where the quarks live on the sides. And between these sites, the links is where the gluons live. And then what we do in lattice field theory is that we calculate all of our observables stochastically using this path integral approach. And the stochastic estimation really means that everything that we calculate on the lattice has a statistical error. So we really have to calculate this path integral over a representative ensemble of gauge configurations. And that has to be a very large one in order to get the statistical error of the observable that you calculate to an acceptable level. So the challenges that we face on the lattice are the more obvious one. Since we are in the finite volume, you would have to extrapolate to match to the physical world, to the infinite volume case. And since we have this finite lattice spacing, if you want to match to nature, you'd have to go to zero lattice spacing. And the generation of these gauge ensembles on which we are actually doing the calculations here, they become more expensive if you lower the quark masses, which means that most of our ensembles are being generated or simulated at unphysical quark masses, and that mandates that you have another extrapolation, which is in the physical quark mass. So this is usually done by employing some types of chiral effective field theory. So these are the very obvious challenges, and these are the very obvious extrapolations. And what I want to discuss also today is the need to control excited states. Is that on the lattice, we usually look at ground state matrix elements that we are interested in, but these are not directly accessible, especially when you are looking at nucleon observables. And I will discuss with you on what the consequences are here. And this is the least obvious of the challenges that we usually face. Most people working on lattice know about this, but maybe to the outside people, this is not very well known fact, and I want to stress it today. So I hope this is something new for you. This discretization is not unique. There are several ways to put the lattice action on the computer, and we here in Mainz, we use this Wilson formulation. It's a 2+1 simulation, so we have two degenerate up and down quarks and a heavier strange quark. And as I told you, this is a very huge effort to get to a decent statistical error, and this means that it's a huge effort not only in human time but also in computer time, and you have to really put a lot of effort also in coordinating things. And we are doing the generation of these ensembles on which we do the actual calculations in a coordinated way in this coordinated lattice simulation effort. And this is a worldwide effort. All the other groups also have larger collaborations where they share their ensembles within the collaboration to do physics. And the physics on the lattice, I will come on the next slide. Just to give you an idea about the ensembles that we have at our disposal here. This is the landscape of the coordinated lattice simulation ensemble. So it's not so nicely shown here in this plot, but here on the left hand, we have the pion mass in both plots. And here on the x-axis, it's the lattice spacing on the left one. On the right one, it's the finite box size. And you already see from this plot here that this region is there is a clear abundance of points, which basically means that this is really hard to do. Unfortunately, the physical point is here. So what we try to do is, in one of the challenges that I just outlined, is we want to go to zero lattice spacing, which means in the x-axis, we want to go to zero. And we want to go from unphysical pion mass to physical pion mass, which means we want to go down here. Okay. Nevertheless, we have quite a substantial number of ensembles at our disposal to do controlled extrapolations in these two directions. And here, maybe I should explain the color coding a little bit. For the finite volume of contributions or corrections on the lattice, there is this general parametric suppression. They are suppressed like e to the minus m pi l. So if you have a m pi l of roughly 4, the corrections coming from the finite extent of your lattice are on the order of a few %. So that is why this 4 is somehow a rule of thumb. You want to stay at 4 or above 4 for this quantity on the lattice to not incur too large of finite volume effects. And this yellow region is where most of our ensembles lie, and this is in an m pi l region between 4 and 5. Okay. As I told you, the physics from the lattice we extract by doing calculations in path integral formalism. And what we're actually doing is we are doing this path integral for correlation functions, where we have some operator creating a particle at position y and then annihilating the particle at position x. And we look at the possible recontractions on the background of the QCD action. And here, what I just show you is this matrix element. It's actually the Fourier transform over the spatial components here. And when you insert a complete set of energy eigenstates, you can get the spectral representation of that matrix element here on the right side. And there you see it has this overlap factor, which is just the ground state to nth energy eigenstate matrix element of that particular operator here. And then you have these exponentials that go with the energy of that nth energy eigenstate and the time separation here. So what you immediately see from the spectral representation of this 2-point function is that for large Euclidean times, or for large Euclidean time separations, I should say, y0 minus x0, you see that the ground state prevails. These prefactors usually grow like a power law in the energy, so these exponentials usually win out. And for the large time separation limit of this sum, only the ground state contributes. And without doing any analytical continuation from Euclidean to Minkowski, you can infer from this Euclidean correlation function already the ground state matrix element of that matrix element that you look at, the ground state energy of that matrix element. The real problem with nucleon observables is, unfortunately, they are pretty nasty in the sense that you cannot wait too long because there is this problem of signal to noise deterioration in the nucleon observables. So for large times, unfortunately, the noise grows for nucleons. And this is why we need to control the excited states in all nucleon observables, or we have to make a huge effort to really control the excited states. And here is an example of this 2-point function where I plot the effective form factor. And you see, if this was only dominated by the ground state, you would just have, unfortunately, I cannot see, wait. Okay, anyway, I cannot see the right part of my screen, I'm sorry. But what you should see at least is that at some time here, it really plateaus to the ground state energy. But before, you have these contributions which are coming from not the ground state energy, but some excited energy states. Okay, and what you should also see on this plot is that depending on the pion mass, the smaller the pion mass, the larger this error gets in the large time region. Okay. Now the 2-point function is already, you already saw that there is problems with the extraction of the ground state matrix elements. But now we are looking at form factors, and in form factors, what we actually do on the lattice is not looking at the 3-point function here, but usually we look at ratios. And we look at these ratios in such a way, we construct these ratios in such a way that for large Euclidean time separations from the source or from the sink, where you destroy your nucleon, that these ratios are proportional to the sought after ground state matrix element. So this ratio here, in the limit of large time separations from the source or the sink, is just proportional to the ground state matrix element that we're interested in. So it's proportional to GE in this case, or GM. Okay. However, what you should expect now is that if you wait long enough, or you stay far away from the nucleon creation or annihilation operator, you should get a plateau, and you can just basically read off again from the Euclidean correlator your matrix element of interest. Now, if you look at real world data, or real life data, I should say, you'd be hard pressed to get a plateau out of this data. So you see at the edges here, there is this rise in the data, which basically means that you have a lot of excited states contaminating this actually expected plateau behavior. Okay. The ways to deal with this issue on the lattice is, in recent years, there's 2 predominant methods, I would say. One is called the summation method, and one is including in this spectral representation that I've just shown you. You include more than just a ground state, and you just include higher order states. And let me first tell you how the summation method works. This summation method is just, you can write any correlation function generically as a function of the time from the source to the sink. And you write it as your ground state matrix element plus some excited state overlap and then this exponential where its exponential is actually damped by the energy difference from ground state to first excited state. And you have the same from the sink. Okay, now to get the ground state matrix element, you'd prefer T to be very large and TF minus T also to be very large, which means that TF is larger than either T or the difference here. So the summation method uses the fact that when you sum this correlator C, which is in this line here, what you obtain from this summed correlator is that your ground state matrix element is now proportional to the source sink separation TF, and it has this additional excited state contributions, but now the exponential is not with T or the difference to the sink, but rather it's just the source sink separation TF. Remember, I told you that this is larger than either T or TF minus T. So just by doing this sum over the correlator here, you already obtain the parametrically higher suppressed representation of your correlation function. And indeed, this is what we actually get in our calculation is when you sum the correlator, for example, for the matrix element corresponding to the electric form factor, you get for these 4 source sink separations, 14, 18, 20, and 22. And you can actually extrapolate, you can actually get the ground state matrix element by just doing a linear fit to this data. And the same is true for the magnetic. Okay, that's one way we deal with excited states. The other was, as I told you, in the spectral representation, you not just keep the ground state matrix element, but you just keep further terms in the exponentials. And this gets very messy for this ratio I just shown you with the square root. This is the ground state matrix element, and then you get additional contributions coming from these exponentials here with energies. Now, in the case of the form factor, these energy gaps between ground state and first excited states are also momentum dependent. And here's the one at 0 momentum. And you get these overlaps, which are in principle, again, momentum dependent. So you can actually go this route and do multi-state fits. Usually you stop here for the 3-point function at an additional state to the ground state, which is a 2-state fit then. But typically you need priors to stabilize these fits. So these are nonlinear fits. You need to fix this gap and this overlap. Or what you can also do instead is you fix this gap and just fit these overlap functions. For the charges, the situation is a bit easier because these in the ratio, the square roots do not appear, and some of these terms just disappear. They do not contribute. So for the charges, you could get away with a different strategy, and I will show you this in the results section. So I'll just show you the result for the Isovector Nucleon Charges from Lattice, and the isovector, which basically means proton minus neutron, is a very nice quantity because they're only the connected contributions contribute. And this is depicted in the sketch here on the right-hand side. And you see that for the charges, the square root factor is just missing here. This is just 1. And you have this ratio of the 3-point correlation function over the 2-point correlation function. And in the asymptotics of large time, this would just give you the charge that you want. In this work, we not only looked at charges, but also at higher dimensional operators. So basically average X or twist 2 operators. And usually the calculations on the lattice are done for several source sink separations. And the largest that one can actually afford are roughly around 1.5 Fermi. And this is just an example of this excited state contributions, and the way to deal with it is on this left column. Is the summation method for the axial charge, for the tensor charge, and for the average X. And you see here that you can nicely fit this linear behavior of the summed correlator to all the 3 charges. And on the right side, you see that you would expect if there was no excited state coordination that there is just a plateaued value, but you see that here there is some bending on the edges. And this depends on the quantity that you look at, the amount of excited state contamination, and it's worse here at the average X point. Now, as I told you, there's this multi-state fit is one way out, but what was shown in this article that I've just shown the slide before, you can also do a simultaneous fit of all these 6 operators, and by extending this data set to more data, you can actually try to fit just this gap from the ground state to the first excited state from data alone without any prior or any fixing the gap. And this was done in this work, and it is a simultaneous fit to all 6 charges actually in this case. So you have dealt with the excited states, and if you had hoped that you're done, this is not true, because you're still facing the other challenges that you need to do the chiral and continuum extrapolations. And usually these are done using fit forms like this. So you have this chiral functional dependence, or the dependence on the pion mass. Then you have a term parameterizing the lattice spacing dependence, A, and you have this finite volume term, which, as I told you, goes like e to the minus m pi l. This power of the lattice spacing, it depends a little bit on the quantity. So we are using order A improved Wilson action, but also the observable that you look at needs to be order A improved. But for some of the charges, this is true already by construction. So for the axial and scalar charge, this correction based on lattice spacing already starts at a squared. For the others, it's not. So you have to take linear terms for the other charges. What was seen in that paper was that the chiral dependence, which means the dependence on the pion mass, is rather flat. And also what you commonly observe in all of these lattice determinations is that the log and this m pi squared term, and they are not really discernible. So you cannot distinguish between this m pi squared log and this m pi squared term. And this was also true in this charges analysis. And usually these types of terms are dropped. This is just to see, if you look at the data, you see that the log looks awfully linear, and then these things cancel each other. Okay, but in general, these lattice artifacts are non-negligible, and you really see an effect here on this plot where there is a bending with the amount of finite size effects that you have here. Okay. Just to give you an idea about the overall error budget, so you invest a lot of time in getting these errors here correct. And the one thing is this statistical error, which is based on our stochastic estimation of the observable that we calculate. But you see that these systematic errors also give you a largish contribution. So if you improve this error, you really need to take care of the other systematic effects. And just to give you an idea of the other lattice determinations of that observable, you see that it's an impressive work that has been put here, for example, by the Los Alamos group. You get a very small error on the scalar charge, and they're all somehow compatible with each other. And the same is true for the tensor charge. Okay. Now let me come to the form factor. So we have this isovector again. So I'm omitting all the disconnected diagrams, which are very hard to calculate. And here I'm presenting you the recent results that we just published 1 or 2 months ago. And here you see the electric and the magnetic form factor as a function of Q squared. And the data points are our most chiral ensemble. It's this E250. This ensemble has a pion mass of 130 MeV. And you see that comparison with phenomenological parameterization of Y, and they match up quite well, I would say. Again, here for the form factor, so this is basically that matrix element at non-zero Q squared. We again have to deal with the excited states, and we do it basically an analogy to what I've just shown you for the charges. Here you see that these effective form factors are not symmetric anymore. You see a steeper rise here to the sink, and you also see you should see, I should say, that for the momentum here, so this is for D200, it's the upper panel, and this is for E250, so this is different pion masses, and the first and second line are different momenta. And what you should see here is that also this is a momentum dependent result, is that your errors are the excited states are also momentum dependent. Okay, you can do this two-state or summation method analysis. The summation method will give you this gray band here, and the two-state fit will give you this black data point. Here, what we did is we fitted actually this ugly function here, and we really fit all of these energy differences and the overlaps.
5 minutes.
Yes. Now, as opposed to the charges, for the form factors, you really need to also map out the Q squared dependence. And there's different ways to do this. And one of the, I would say one of the very, one of the ways that is being done most commonly is the Z expansion. But in this work I just showed you, we used a different route where we went to directly fit the form factor using chiral effective field theory. But nevertheless, I will just tell you what the Z expansion fits do. It's basically just a fit of this functional form of GE and GM for every ensemble. And you can do it by performing this Z expansion, which is this conformal mapping of this variable T to this variable Z. And I think to summarize, the Z expansion is just if you were to do a Taylor expansion with this within this variable T, you immediately see that your expansion radius of convergence is somehow limited by this threshold here and this cut at the real axis for 2 pi. And the Z expansion tries to avoid this, this issue. And then for every ensemble, you do the Z expansion. So you get for every ensemble, you get the magnetic moment, the radii, and you get these points for every pion mass. And then you can do the chiral extrapolation using this data. But just to remind you, you have a lot of data for Q squared to just get this 1 point here for E250. Okay, now this red point is, of course, there is no isovector quantities in real world. So what we did here is we took the PDG values for proton and neutron and combined them to give the isovector quantities. And now I just want to show you the direct fits that we do. So instead of doing this intermediate Z expansion to parameterize the Q squared behavior, we use these chiral EFT expressions to directly fit the data at the different pion masses. And this is one of those fits that we obtain here. So in this sense, this is a simultaneous fit in Q squared and n pi squared. And as such, we avoid this intermediate expansion altogether. And also for the form factors, we do these systematic games where we introduce lattice spacing and finite volume. We do it in 2 ways to really see if this is giving you a different contribution here. And we actually do this with different pion mass cuts and different Q squared cuts. And what we end up with for the isovector vector form factor is these values. So you see that we reproduce the magnetic moment here. That's the blue point rather well. So there is no chance of getting as precise as experiment here. And for the electric radius, you see that this cross here is the PDG value of the proton and the neutron combined to give the isovector radius. And the same is true for RM here. Now this squared is if you just took the proton radius from the Mainz data and combine this with the world average for the neutron radius. And this is the point you would get for the isovector electric radius. So you see we really favor this smaller value of the electric radius. You can turn our calculation around. You can take the information from the neutron radius and take our isovector result, and then you can infer the proton radius that you would get out. And this is the value for our best estimate here based on these numbers. Okay. What's interesting here is that it's the exact opposite for the magnetic radius, where we are in favor of the Mainz result as opposed to taking the all-world average. Okay, well, I hope that I've shown you that the lattice determination of hadronic observables, the precision is picking up also for nucleons. And with this increase in statistical precision, we really have to take care of the other systematics like extrapolations and lattice spacing and finite volume, but also the excited states. And I have not discussed a lot of other observables that we are actually able to do and will do in the near future. Thank you.
Thank you very much for this very nice overview. Are there questions or comments? Then let me start. Can you go back one slide where you show the results also in comparison with the results from the other groups, the other lattice groups.
Yes.
What is different in these different calculations from the different groups?
Yeah, so there's different actions involved. So it's a different discretization. That's one point. It's also a different way of dealing with excited states, as I've shown you. Some do multi-state fits, some fix the gap. And really is this treatment of the Q-squared dependence is also different. So usually what is done is this Z expansion, and then you extrapolate the Z expanded results. And this is different in this work here. We really do fit directly the electric and magnetic form factors using chiral EFT. So I'd say this is one of the major differences. Also, one has to say that some of these determinations, they are not even trying to do certain extrapolations. So they are done at physical quark mass, for example. So there's no chiral extrapolation needed, obviously. But there's a lot of difference in the treatment of excited states, I'd say. This is
are there, I mean, for the high precision calculations, there is the flag effort to rate the different lattice calculations.
Yes.
Is there a similar effort to do this with these type of observables?
Yeah, I think so. Yeah, I mean, you've seen this for the charges. I'm not so sure if there's something for the radii, but yeah, I mean, the problem here is that this is a derived quantity, so you have to do this derivative for the radii. So I'm not so sure if this is really comparable from one lattice group to the other.
Okay, but of course this is very helpful for non-lattice specialized to assess the quality.
Yeah, absolutely. It's really hard to tell who's doing what. Yeah, I understand. Yeah.
Okay, there is another hand raised. Guy, please.
Yes, well, thank you for this very clear presentation. Just a general question, what are the challenges in the future to go to time-like for the form factors, or is this impossible due to the Euclidean, or shall we need to wait for quantum computers to do it in real?
Yeah, I think.
Thank you. I will very.
Sorry, I interrupted you. I'm sorry.
No. I am very curious about this point. Sorry.
Okay. For this, whenever you have thresholds coming up, and I think it's very hard for the lattice to do the calculations directly. So, for example, if you imagine scattering experiments is not directly doable on the lattice because of what you said, this Euclidean rotation. So we are in imaginary time. I have a strong feeling that this is true for the time-like form factor, but I'm not so super sure. I have to admit, I'm not an expert in the time-like form factor on the lattice. I would have to get back to you on this issue. But I can imagine it's not so easy to do.
Yes. Okay. Thank you.
Probably some well-constrained extrapolations would be.
Yeah, I mean, you can at times you can get away with tricks, like Lucia formalism instead of doing the real scattering experiments, for example. I'm just not aware of. You have a very interesting point in the time-like form factor. I just don't know. You can, of course, analytically continue using some dispersive approaches, but yeah, this is not a direct. I think you were interested in the direct determination and not some dispersive thing, right? So,
yes.
Yeah.
And also for a dispersive to make sense, you need data going through large values of t.
Yeah. And large t is not possible for the lattice. I mean. Yeah, you're right.
Okay, thank you very much.
Okay, let's move the remaining discussion to the discussion session afterwards. Thank you very much again.